Welcome to our discussion on unit cells, which are fundamental to understanding crystal structures. Think of a unit cell as the basic building block or blueprint of any crystal. Just like how a brick is the basic unit that builds a wall, a unit cell is the smallest three-dimensional arrangement of atoms that, when repeated in all directions, creates the entire crystal lattice. The unit cell contains all the essential information about the crystal structure, including the positions of atoms, the distances between them, and the angles at which they are arranged. Understanding unit cells is crucial for materials science students as it helps explain the physical and chemical properties of crystalline materials. Welcome to our comprehensive study of unit cells in crystallography. This table of contents outlines the key topics we will cover in understanding the fundamental building blocks of crystalline materials. We'll start with the basic definition of unit cells and explore their key features. Then we'll examine the different types of unit cells and the 7 crystal systems that classify all crystalline structures. We'll also learn practical calculations for determining atomic content and conclude with the real-world applications in material science. Each section builds upon the previous one, providing you with a solid foundation in crystallographic concepts essential for materials engineering and chemistry studies. A unit cell is essentially the building block of any crystal structure. Think of it like a single tile on a tiled floor. When you repeat that one tile pattern over and over in all directions, you get the complete floor covering. Similarly, when unit cells are repeated in three-dimensional space, they create the entire crystal structure. The unit cell is characterized by 6 parameters, 3 edge lengths called A, B, and C, and 3 angles called alpha, beta, and gamma. These parameters completely define the shape and size of the unit cell, which determines the overall crystal structure. The unit cell is fundamental to understanding crystal structures. Start by explaining that lattice points mark where particles are located in space. The 3 edge lengths A, B, and C define the cell dimensions, while the 3 angles alpha, beta, and gamma determine the cell shape. When counting atoms per unit cell, remember that corner atoms are shared by 8 cells, face atoms by 2 cells, and body-centered atoms belong entirely to 1 cell. Visual models are essential for students to grasp these three-dimensional concepts effectively. Unit cells are the basic repeating units in crystal structures. There are 4 main types based on where lattice points are located. Simple unit cells have points only at the 8 corners. Body-centered cubic or BCC has additional points at the geometric center. Face-centered cubic or FCC has points at all 6 face centers plus corners. End-centered has points at 2 opposite face centers and corners. Understanding these types helps predict material properties. Crystal systems classify all crystals based on their unit cell geometry. The 7 systems range from high-symmetry cubic systems like table salt and diamond to low-symmetry triclinic systems. Each system is defined by specific relationships between the 3 unit cell edge lengths and the 3 angles between them. Understanding how to calculate atoms in unit cells is fundamental to crystal structure analysis. The key concept is atom sharing between adjacent unit cells. Corner atoms are shared by 8 cells, so each contributes only 1/8 to any single cell. Face atoms are shared by 2 cells, contributing 1/2 each. Body center atoms belong entirely to 1 cell. The general formula accounts for all positions. Corner contributions plus face contributions plus body contributions equals total atoms per unit cell. Unit cells are fundamental building blocks in material science that serve multiple critical purposes. They allow scientists to predict important physical properties like density, melting point, and electrical conductivity by analyzing the atomic arrangement. X-ray crystallography techniques rely on unit cell dimensions to identify unknown materials, making them essential for material characterization. These concepts are widely applied in studying metals, semiconductors, and salts. In modern research, understanding unit cell mechanisms is the foundation for nanotechnology and designing new materials with specific properties.